simulation tools for implementation of power electronic systems. In general, we all know that there are many simulation tools available for electronics, and even other different electrical domain like power system, maybe microelectronics, VLSI, etc. So there are certain differences, because when I say, or when in a general sense we say that okay, we want to do simulation, right? We'll see what do most of us knows what do you mean by simulation, what is the importance of simulation and all, but it is like simulation for what, right? Simulation may be for a mechanical thing, maybe a mechanical design, maybe for some civil structure, maybe for a business enterprise plan, maybe for a strategy explanation, or maybe let us say for an electronics circuit which runs on very small amount of voltages and power, or maybe currents. It may be for power electronics, it may be for high frequency, and there are many other things. Simulation in general is a very, as such is a very generalized term, right? So in this session, we'll particularly focus on simulation tools for implementation of power electronic system. So which are the best simulation tools or softwares available which we can select for power electronics, right? Because there are many software, like best one is the basic thing that we know, SPICE, right? It was a software which was introduced way back by university, way back around in 1984 or something, by University of Rodrigues. Like it was back then just used for small electronic circuits and all. And nowadays it has progressed a lot. So we'll in this journey, in today's session, we'll see that which are these softwares, how are they useful, and the most important thing is that how these softwares interconnect with each other. Because today is an era, like I remember I started learning these softwares when I got into my bachelor's undergraduate program way back in 2005. I remember I started using this SPICE software, specifically PSpice software, and we started learning this simulation things, that what is simulation, how it can be done, and we were like, we didn't knew anything. We had just started, and that was a time that we had to simulate that thing on those old PCs, and the simulation took a lot of time. Even just if I want to simulate a small rectifier, it would take so much of time, right? But these today or these days is an era where it is not that you're not limited to one software. Software availability is not a problem. Even if the softwares are licensed, you can get free trial versions or maybe student licenses. Even if you request the manufacturers or the not to say manufacturers, but the companies who are licensing these softwares, they also give you such kind of licenses free of cost as per your request, right? So these are all the things. So these days we have so many number of softwares, and it may happen that thinking of our side, we are in academics, but industry people, right, who are working in industry, or maybe our students who are the future resources for these industries, right? We are the ones who teach them softwares, or maybe theory is a secondary part, but if we talk of software, the simulation software, maybe these practical things, we are the ones who teach them how to initialize, how to go with these things. So there it goes, that we have so many number of software these days available, and if we don't know that what to select, which software to select, which tool to select for which kind of design, which kind of circuit, which kind of implementation, how are we going to be sure that our students will learn it properly, and how are we going to make it sure that those students, while they work in industry in future, they will work properly. Right. I remember many of my students are like placed in various companies all around. One of my student was in or is in, I can say, G Bangalore. Right. She is working on this coding and simulation kind of software. So there, at such points, I keep on getting feedbacks from them that it was it was the reason that they learned this software back in their undergraduate program. It is helping them to properly implement it in the industry, and they're getting a good growth at that point. So let us start with our session, simulation tools for implementation of power electronic systems. I hope I'm audible. My presentation is visible properly. Abhishek sir?
Yes, sir. Yes, sir.
Okay, fine. Because I'm not, it's in the full screen mode, so I'm not able to see other things. Okay, so this is a screenshot. I just thought of taking it from Agrawal sir's presentation, the first presentation we had in this FDP. Like we all remember, sir has explained nicely the basic block diagram of a power electronic system. Actually, I had also included it, but thought of taking this. So here we know, just let me select the pointer. Yeah. So we all know that in case of power electronics, we have this electrical input, or I can say supply. This is a load, right? So this is the thing we have. This is the thing we want to supply, or maybe to control, right? Not control exactly, but we want to supply the desired amount of power to, and this is the power converter, right? Which contains some kind of passive elements and maybe switches, and based on their configurations we have different converters, right? And of course you have a control signal from a controller which controls or regulates the behavior of this controller. We all know this thing, right? So what does simulation gets involved into? Simulation mainly involves into design. Once you have designed this power converter, it can check the behavior of this system power converter. It can also it can also be helpful to design a controller, because if you make a power converter hardware and directly design some control, right, load it in a controller, maybe analog, digital, whatever, and if you directly give to the converter, it may blow up the converter, it may not be able to operate properly. So every time doing that is a tedious work and a risky work. So that's why we prefer simulation, and simulation will help us to implement or maybe check the behavior of this power converter circuit, controller, maybe both together. And apart from that, we have some other things also we'll see, right? So as I told you, this is the same diagram which I was going to explain. So we are interested in these two things, controller and power electronics converter, how we can simulate it, how we can get the results. Rest things, electrical power and load, are the basic things which we take supply from and give supply to. And apart from this, we have many subsidiary circuits, small or large protection circuits, maybe some feedback circuits, sensors, right, feed-forward circuits. We may have some monitoring circuits and etc. There are many other parts which which cannot be shown in this diagram as such, right? So power electronics converters, we know that there are mainly 4 types of power converters: AC-AC, AC-DC, DC-DC, and DC-AC. Controller, if you see the part of controller, there are many types of controllers: analog, digital. In analog control, or in analog control part or controllers part, I can say it's passive based controls, or maybe some IC based controls. Digital controls includes microcontrollers, DSPs, single and multi-core, maybe FPGA, right? So now when we talk of this thing, implementation of power electronic circuits, as the speakers earlier, right, everyone has said that it's an iterative process, right? Whomsoever you quote, everyone will say the same thing, and those who have also worked in this field, we better know that it's an iterative process, right? It's not that you are going to design something on paper, you're going to assemble it, and simply you just give the supply and it will run. No, it is never that. Right. I remember one of my friends, my colleagues, quoting one saying, because some of our students, like one of the good student came to us. He said that, sir, I want to implement this thing. It was some amplifier circuit, as I remember, some audio amplifier circuit, and he just wanted to implement it as a part of hobby project. And he told us that, sir, I want to implement this. So this is the diagram. I'm assembling it and it is not running. So that time I remember him quoting the student that designing a circuit or maybe implementing it is not a one-time task that you take it from somewhere, copy it and make it. Because if this thing happens, right, there are many electronic circuits, many designs and etc., many other things already given ready-made on the internet, maybe on different websites, etc., where you get everything right from the initial design to the schematic to the design parameters, bill of material, maybe PCB design, everything. But it is not that you just assemble it or procure the components, assemble it, solder it, make the PCB, and give the supply and it will run. No, it is never that. Right, you have to study every component in detail, and accordingly you have to implement it, and then that circuit will work. So it's like the first thing that we see here is the theory and idea, that what you want to make, that is the first idea. Let us say, for an example, I want to go for a multi-level converter for, let us say, some motor or maybe for a power supply or something, anything. So that is the idea, and behind that idea you go with the theory. So let us say if I want to go with multi-level converters, I need to check that what kind of multi-level converter do I want to make. Right, a simple one, line capacitor, H-bridge, maybe diode clamp. Then after selecting that topology, just going through the theory and everything, then we go for some paperwork, right? Where we finalize our design parameters, etc. Then we go for component selection, the final the design of the power circuit, right? What kind of components will require, what kind of power circuit will require. Of course, apart from that, here other things are also involved which I have not mentioned in details, like protection circuit, maybe some other interface circuits, etc. Then the major things, I have mentioned here. After that, we come up with control selection and design. Right, this is a very important part apart from the power circuit design. Then we go for a simulation with all those design parameters, maybe all those designed control circuit. Right, we simulate it. So that simulation is an initial simulation. Then we see that what are the simulated parameters, what are the outputs, what are the control parameters and all. We'll try to manually see what is the error, what correction do we need. We may correct it, we may make a final simulation, right? We may correct it again. I'm sorry, I think this step should be interchanged. Right, and after that we go for a PCB design. Right, we may go for, in between we also may go for the basic check of a hardware on, let us say, breadboards or maybe on a rough board, and then we can go for PCB design and this thing. So hardware layout and PCB design are again correlated things, and finally we'll assemble it. Once the PCB is designed, we'll again test it. We'll have to test it. We'll have to see whether all the parameters are in line or not. And if you remember Dr. Amit quoting yesterday, right? He said that they had made one inverter for, they had made one system for 3 kilo, and they had he had tried to implement it first with just work for 22 watts, right, instead of 3 kilowatts. And after few iterations, after few corrections, after a few corrections, or maybe what should I say, that some measures that they had to take into account, they changed it, they minimized the noise and other things, and then those people were able to finally get the output up to the mark, even though the component selection, design and the control selection was all right. So this is the whole iterative process. Now in this part, control selection and design, simulation, and PCB design and hardware layout. These are the three things which involves proper design tools or simulation tools, I can say, or automation, electronics automation tools, which can be very much helpful to us while designing our circuit. Right? How we'll see that, and why that also we will see. Right? Because control selection, of course, and as we all know, all these things involve a pure mathematic behind it. Even if you go for control selection, even if you go for component selection or anything, everything is based on mathematics. And all these softwares, whatever simulation softwares, the base of these softwares is basically modeling or mathematics, right? So as I told previously also, our sessions focus is on simulation tools and software which are available or which can be helpful to us specifically for power electronic applications, or more specifically for power electronic applications, for controller design, simulation and testing, for the simulation of general circuit, power circuit, or maybe the whole circuit as such, and PCB design tools. Right now, before moving ahead, let me brief you one thing. That simulation tools for power electronics, if I say in general, you will agree that okay, simulation softwares which can draw schematics, simulate it, give us waveforms, maybe check our controller, maybe help us in designing a controller. Those softwares I can justify under simulation tools for power electronics. But what about PCB design tools? Why? What is the reason I have included PCB design tools also in simulation tools for power electronics? The basic, can anyone tell me like what can be the reason why we are considering this PCB design tools, right? Any kind of softwares or tools for PCB design, very important in power electronics. Yes, can I get some feedback from any of the participants? Is anyone? If you remember,
for compactness.
For compactness, actually PCB design, the reason we do PCB design is of course the compactness of the whole product, right? It may be an electronic product, maybe a power electronic based product, or maybe an electrical product, depends, right? Like for example, I can tell you, of course, answer is not, I'll not say it is wrong, but if you just observe this thing, Bluetooth antenna, right? The one which Amit sir showed yesterday. Uh, Previous days, Bluetooth used to be a pen drive size device, that USB Bluetooth. Nowadays, it is just like a small USB attachment, which even you cannot even see, like the adapter of a mouse, wireless mouse, right? So that is okay, correct. We use these PCB design tools for that thing, but with reference to power electronics, I'm talking with reference to power electronics. What is the specific importance of PCB design tools with respect to power electronic circuits?
To avoid parasitic elements.
Okay, correct. Maybe to avoid parasitic elements. Any other answers?
Electromagnetic interference.
Yeah, correct. Electromagnetic interference, and it's it's checking and all, right? That what is the EMI, EMC of the device? How much it is compatible? How much interference it is generating? Right? Is it within limits or not? What else?
To reduce losses.
Okay, to reduce losses also an answer. There is still one more point which I am looking if I can get from the participants. Because that is the thing. See, if we understand this thing, that what is the reason why we are selecting these tools, why we are going with these tools, what is the importance, then only we'll be able to enjoy using it, learning it, or maybe applying it. Okay, let me tell you. These all answers are absolutely correct. EMI, EMC compatibility, maybe to reduce the harmonics, maybe to reduce the interference, noise generated in the circuit, to reduce the main reason behind selecting a proper PCB design tool and using it in power electronic circuit is that power electronic circuits, as we know, combine two things. One is the low power circuit, one is the high power circuit. On the other hand, may be a low frequency circuit and a very high frequency circuit. It may be low power, and that means a low voltage, or maybe a different frequency circuit. So for example, if I'm implementing, let us say, an inverter, a very basic inverter, and suppose the switching frequency of the inverter is around 100 kilohertz. So 100 kilohertz is that one part. The controller is switching at generating those pulses at 100 kilohertz. Those we are passing on to the various switches of the inverter, and ultimately the output of the inverter is at 50 hertz, right? So if we see those things, so here many frequencies, many different power levels, and such thing gets involved. So when we go for PCB design, as you remember in the previous sessions, we saw that circuit in power electronic circuits, components interfere with each other. There are some cases those two need to be taken while designing your PCB, right? Sorry, while designing your this thing, what we say, controller part and this power circuit part, and you need to take care that when you mount them or when you operate them together, like until unless you simulate or maybe design a controller part separately, it will work absolutely fine. When you design your power circuit separately, it will work absolutely fine, right? Maybe you design your protection circuit, sensing circuit, and all these things. Everything will work fine on its own, or if you just test it with a single component. But when you keep all these things together, right, then comes all the issues. Even if your circuit design is complete, even if your all the parts, every design, every component selection, and everything is perfect, right? Even though the circuit will not work, right? It will not work as expected. Maybe it will not work at all. So there comes the importance of PCB design tools, and there comes the importance of the PCB design learning by an engineer, right? So if you are doing some research for your product, so it is you who know the best that what kind of PCB, what kind of layout do I require for my project. We'll see that in the coming things, right? So as I was talking, we have this electronics part for which various simulation tools are available. Then comes power electronic circuits and control, which we are focusing for. And in the end comes product support, including all parameters. That means once the circuit design is complete, you also have to take into consideration the whole product design, the mechanical part, the aesthetic part, everything, the cost factor and other things, right? Let us see what is simulation. It is, we can define it as a way to model real life or imaginary situation to study its behavior working under specified situation. So we can, simulation is basically a way to implement real life things virtually, or maybe some imaginary things or imaginary situation which you may not be able to implement physically, right? So simulation of power electronic circuits or power electronic systems, right? When we talk about compared to basic electronic circuit. So what is the difference? What are the challenges? So basically simulation of power electronic circuits is made challenging by these following factors. First thing, a very important thing, extreme non-linearity is presented by the switches. We know very well because hopefully all of us are electrical engineers or maybe electronics engineers. We know one thing for sure, right? If we work in electrical domain, pure electrical domain, it's like all the things are conductors, right? Conductors are conducting electricity and we are distributing it, maybe generating it, maybe utilizing it, whatever. Second thing, if we go to the other end, it is non-conductors where electricity does not conduct and it's out of question, right? Third thing is in between of both of them, that is semiconductors, and that is where electronics starts, right? And with electronics in picture or with semiconductors in pictures, like maybe diode transistors and all, right? There comes a border where non-linearity may start, because as we see, if you look at a transistor, BJT, power BJT something, you'll see that BJT, if it works in active region, it will work as an amplifier, right? And it will behave linearly. So no problem till then. So this is electronics part, where electronics and communication discipline comes into picture. And most of these devices work in active part as an amplifier for the communication purpose and all. That is up till then, everything is fine because all the things work in linear domain. And until we are in a linear domain, everything is good, everything looks a nice picture. As soon as we study transistor as a switch, that is, as soon as we move to the saturation and cutoff region of the transistor's characteristics, we'll see that now the nonlinearity starts, right? And from this part, so then maybe you consider whatever switching, power BJTs, power MOSFETs, and other things. At that point, this nonlinearity comes into picture, and then it does not behave as expected. Like for example, if you have let us say a car which is going on a road, right? You can basically predict that, okay, if the driver is steady and sound and everything is good, the car will go on it will follow the path and it will go on the road. But you cannot predict a child who is just started running or just started learning running and all, walking, running, whatever. You cannot predict in which direction he or she will go and what he will do. So that kind of behavior is basically nonlinear behavior. So this is the very big challenge that we see in case of simulation. Next is time constants within the system. It may differ by several order of magnitude. So in power electronic systems, generally the time constant within the system itself, they have a very vast difference sometimes. As I told you, if you just take the case of a frequency itself, right? Just the operating frequencies. As I told you, there are various frequencies in which in the same system, which may be there may be different subsystems in a power electronic system, which may be working at different frequencies at the same given time, right? Third is, and even the time constants of different systems may be different, and they may be different with a very huge amount of magnitude difference in them. And third is lack of model. This is a very, it was a very common problem till now, I can say. Till now in the sense, till recent years. Because I remember around 10-15 years back, availability of models was a very big problem. But these days, this problem has started coming down because many of the paid softwares, they are nowadays giving us ready-made models. Even the companies which are manufacturing these switches, right? The manufacturers, let us say ST Microelectronics, maybe Texas Instruments, or other such kind of manufacturers who are manufacturing these semiconductor devices, they themselves these days give ready-made models for their switches. So these kind of things are easily available on internet these days on the websites. It's due to the availability of internet and other things, right? So that's what simulation is, and that's what simulation of power electronic circuit is, that why it is challenging and what is the reason that we are going to study some softwares and specifically implement only some softwares for our systems, right? So we'll see those reasons. We can see, and basically simulation, we can conclude that simulation solves real world problems safely and efficiently. That is the basic goal behind this thing, right? So now, if you see in power electronic simulation, as I was talking, we are going into switch, the cutoff and saturation region of the switch, right, or of the transistor, or we can consider any of the switch. So here you can see ideal switch. Now simulation, when you do, most of the electronics or other simulations involve ideal switch. So when you simulate an ideal switch, right, how does it behave and all, we'll see. See, this is an ideal switch. This is an open switch. This is a switch. This is an open switch. This is a closed switch. Open switch means it is totally disconnected, no current flowing through it. Close this, current flows through it. It is full current flows through it, and ideally zero resistance. So when a ideal switch you consider in short circuit condition, it has got zero impedance while it is closed, and in open circuit condition, it has got infinite impedance while open, right? Whereas if you consider a non-ideal switch, the one which we actually use in power electronics, because no switch in this world or nothing in this world is ideal, as we know, right? So the practical switches which we use, right? These are basically, these look something like this. So when you have a switch, you can show it like this, but when it is an open switch, it is not actually open. As you remember yesterday, Amit sir's session, he also said, and before to that, in other sessions also we had seen that. Sorry. So that while practical implementation, we have to take care of these parasitic elements, right? The inductances and capacitances. So ultimately, an open switch behaves as a capacitor. A closed switch behaves as an inductor, right? Small inductance is always present when the switch is closed, and a small capacitance is always present when the switch is open, right? If you remember, Dr. Sujit Biswas, he also had focused, or he also had told us how these all parasitic elements come into picture and how we have to take into consider these things, right? So if an ideal switch is connected in series with an inductor, right? Imagine this is an ideal switch. This is an open ideal switch, and you connect an inductor here, right? You connect the inductor here. Tell me what will happen. It will degenerate the inductor and reset its current to zero. Why? Because it will forcefully not allow the inductor to conduct even though it is charged, and ultimately it will degenerate it, right? Similarly, if this is an ideal closed switch, right? So if this is an ideal closed switch, now you imagine you connect a capacitor in parallel to this switch here. Just imagine you have a capacitor here. What will happen? The capacitor will be will be subjected to a direct short circuit, right? And due to this, it will now degenerate the capacitor and reset its voltage to zero, right? So we cannot have such kind of conditions or such kind of things in practical power electronics, and it is as such beneficial that we don't have an ideal switch or capacitor switch, or even in either in open mode or maybe closed mode, right? So in case of a non-ideal switch, as we know, every non-ideal switch has got a parameter resistance, right? Every switch has got some resistance, and based on that resistance, if the switch is in open condition or maybe closed condition, you can, while simulating or while doing some mathematics, you can define that what can be the inductance of that open switch, closed switch, or what can be the capacitance of that open switch using these basic formula, that L is equal to T into R, where T is the simulation time step of the software or of the simulation that you're using, right? So these are the things that we have to consider in case of power electronics, because if you do the simulation of any power electronic circuit, maybe a DC-DC converter, rectifier, inverter, anything, right? Maybe a buck converter, maybe a motor drive or anything. If you try to do it using ideal switches, you're not going to get accurate results. You are going to be, your results will not be accurate for sure, right? So now
Sir,
let us come.
excuse me,
Yes.
sir. What is
Yes.
the value of R there?
The resistance.
Which resistance?
The internal resistance of the switch. This R generally can be found out from the data sheets.
Okay, sir.
Right. So if you consider, let us say, a MOSFET, you can find out the internal resistance of the R-on of the MOSFET, right? So that resistance can, this is particularly for a simulation software if you are working, right? So these are the internal calculations that it do. But the part that I'm showing here is for understanding that what is non-ideal switch, how does it behave, how these capacitances and inductances will change. When I say that this T is the simulation step of the electrical part, you can assume or you can imagine that as your frequency also changes of the operation, right, for the switch or of the whole system, right, these capacitance and inductances value will also change, and that is where we need to take care. Am I clear? Yeah. So now let us come to the heart of this presentation, simulation tools. So see, there are many simulation tools. These are just some limited simulation tools that I could, find out and maybe integrate. And to be very frank, I am also not, expert in all of these softwares. To be very frank, because you may be using 2 or 3, 4 or 5 softwares for different purposes. My main objective here is to introduce you to various softwares available, which you may use for different types of projects or different types of your projects, depending on the application and depending on the requirement. Right? We'll see this. So you can see here, as I know or as I believe, most of you must have heard the name, or most of you must be using Matlab because it's a very common software, right? I don't believe that there might be anyone here who has not heard the name of Matlab, right? Even this may be true for, I suppose, PCM. Is there anyone who does not know what PCM is? Just just a query, like, is there anyone who does not know what is PCM? I think it's also a very common software, or maybe most of the people use this PCM, right? But apart from that, there are many softwares: Plex, Nsys, PSpice, Orchid. PSpice Orchid is also very PSpice is also a very common software that most of the people know, but still, I believe that most of you might not have used it. Then you have LabVIEW, Multi-C Multiboard by this is National Instruments. Then we have Octave, Scilab. You might also have heard the name of Scilab, I believe. Then you have Julia, Maxima, Spice. Spice is the very basic software from which this PSpice was developed. Then you have LT Spice. This is Linear Technologies developed software. You have NG Spice. You have Tina. Tina is I think used by Texas Instruments. Okay, it's a proprietary software, but Texas Instruments mostly uses this software and gives models for this as well. Then you have Circuit Maker, KiCad, Design Spark. These are all PCB, mainly PCB making softwares. Then you have this OpenSC, CPEC NG, Simulite, Naga Ide, GURB-V. This GURB-V actually is GURB Viewer. This is specifically for viewing Gerber files. You'll see that. I'll tell you in the end. Sage Math. It's a pure, mathematics-based software. If you know, some of you might be knowing that Mathematica, which was used to solve basically linear differential equations, maybe ordinary differential equations, maybe this differentiation, integrations, etc. It is based on that only.
Sir, I have one question.
Yes, please.
Sir, is there any simulation tool which provide the small signal modeling? Yeah, small signal and
yes,
small signal modeling or small signal analysis, sir.
Yes, small signal modeling can be done in this PSpice Orchid, right? This Spice software. Maybe this Multisim also gives you option for that. But PSpice is a very commonly used software for small signal modeling. Spice software is basically, it was actually developed for these only, electronics and small signal modeling only. You can do this small signal modeling in Orchid, Spice, and this kind of softwares. Right. I will discuss this as it goes because I'm going to discuss all these softwares in a very quick fashion, and maybe we'll guide you where you can find the resources for this, so you can start working on that if you want. Okay.
Okay.
Yeah. So these, you can see the red ones are basically paid softwares, right? This red Matlab, Plex, PCM, Nsys, Orchid, LabVIEW, Multisim, Tina. These are all paid softwares. You need to pay for them for a full version or maybe for those kind of versions. And most of these softwares these days are providing, for academic use, I can say they are providing student versions, trial versions, demo versions, where you can get the full functionality of the software, but with limited amount of resources, right? I'll tell you one by one when we go visit these softwares. Okay. This is a screenshot from Wikipedia. You can just Google up Wikipedia for a list of free electronic circuit simulators. Right, so I have just included this screenshot for your basic understanding and knowledge. You can see there are many other softwares also: KTech, KTech Lab, Logi, Sim Evolution, LT Spice, Microcap, NG Spice, Books, Sapwin, Spice, Tina, PSpice for TI, and Size. So these are the different developers for these softwares, right? And these are free. These are free. Tina, as I told you, Tina is a design soft proprietary software. You can purchase the license for this as well. It is as well as it is also available free for online designing on Texas Instruments website, right? So you can see the latest releases. What is the current development source? Which are the platforms supported? Most of the platforms support generally this Linux as well as Windows, so that is not an issue. Because Linux lovers can also use this. Windows lovers can also go with this software, not an issue, right? And these notes will help you understand that which software is used for what, right? You can see KTech Lab is a Linux-based software which simulates a PIC microcontroller, right? Then, yeah, this NG Spice is a very popular software which you can integrate with Altium Designer, or which is integrated with Altium Designer, Eagle, and KiCad. I think I missed Altium in this list, I suppose. Yes, I have not included Altium here, but Altium is also a very popular software for PCB design, right? And so this is just for your information. Now let us see some of the open source softwares. Circuit Maker, a free to use open source software where you can create schematics and basic PCB, right? It's a free software and it's a basic software which can be used to make small PCBs and all. This might not have that much importance in case of power electronics, but if you want to use, or let us say make small PCBs, small circuits, right? Or maybe you want to teach your students for to make PCBs or just for the start, you can use this. You can even use this open source schematic editor to make basic schematics and include somewhere, right? OpenDesignCircuit.com. This is a website. You can see it's a repository for various open source electronic design automation softwares like Magic, IRSim, NetGen, PCB, Xcircuits. Right, you can give a visit to this site later on. Next, you have KiCad. KiCad is a very important software. It is basically a schematic editor and PCB designer software. We have I have included details. I think later on I'll discuss it. Okay. Then you have SQL. SQL also I have included the details later on. It is basically a general purpose circuit simulation package. And sir, you were asking me, you can also simulate this. You can also use this SQL, which is developed by Professor M.B. Patil of IIT Bombay Electrical Department. It was developed in IIT Bombay and it is available on free of cost on the IIT Bombay website. You can also use this for this small signal analysis. Minimum, I think this can be used for this small signal analysis, no?
SQL, small signal, I don't know, but then circuit simulation we can use.
Yeah, for circuit
small
simulation.
Signal I have not tried.
Yeah, because I also not tried this small signal analysis in this. That's why actually I just confirmed it. Anyways.
But this is like a mobile app, no? Mobile app.
No, it is available in mobile also, and I think on for PCs also.
Okay, fine.
It's available now. I think previously it was only for mobile, but now I think.
Okay.
I have included some screenshot later on. We'll see that.
Okay.
Yeah. Then you have this Naga Ide. This is a less popular software, but this is popular among free or open source users who are working with C++ and Python. The main feature of this software is that it includes a Verilog, Naga.Verilog, which is a Verilog parser, right? So that can be used in case you are working with Verilog. Then OpenSC is again a circuit design software, right? It has got a nice and efficient GUI, which is basically used for designing linear electronic circuits, right? This OpenSC also, sir, you can try for this small signal analysis if you want. I'm not pretty sure, but since this is a linear electronic circuit software, it may have that feature, right? Similarly, you have this QSEPEC NG. This is Qt based symbolic analysis program.
Sir, this open source software are
Open source softwares
also
are
providing the hardware interface.
Might
Also
be
providing the hardware interface.
Might be in some case, might not be, but these small open circuit softwares will not provide generally this hardware interface, because see, I'll tell you all, this is a very basic and understandable fact that when it's an open source software, until and unless you don't have some donors or maybe some investors who are investing in for free of cost, it is very difficult to develop all the features and everything, right? So might hardware interface in all of the free circuits, free softwares will not be possible. I suppose there are certain softwares like this KiCad. If you see, this is not for simulation, but this is for PCB designing and all. But if you see this KiCad, the open source community for KiCad and one more software is there. For those two software, the open source community is very huge and very large, and most of the people are using this software. So here you will get all the kinds of resources for PCB design, but the same may not be true for hardware interface in case of open source softwares. For hardware interface, you must have to go with some of the paid softwares depending on your application. So then you have this Simulide. Simulide is again a circuit simulator software which allows you to test your circuit before prototyping. It's a simple real-time electronic circuit simulator intended for hobbyists or students. You may ask your students to go for this and do some experiments using microcontrollers like PIC, PIC, or maybe AVR, Arduino, etc. Right. Next is GURB-V. GURB-V is GURB Viewer. GURB Viewer is an open source Gerber file viewer for RX274X formats. Generally, when we make this PCB, right, the PCB files, the design files of a PCB are called Gerber files, which includes the top layer design, bottom layer design, solder mask design, the through-hole component design and everything. So those files are called Gerber files. And to view those Gerber files, like in case of an image, let us say, image or maybe in PDF format, you require such kinds of software. So GURB Viewer is a very commonly used open source software for that. That's why I had preferred including this here. And SageMath, as I told you, it's a Python-based scientific library-based software to use to analyze data sets in mathematics. It's more of a mathematical kind of software. So now let us focus on the major softwares which are used and where you will get almost all the features, right? Starting with Matlab, it's a very common software we know, and it's a very widely used software. Why? Because Matlab does not focus only on power electronics. Matlab does not focus only on electronics circuits. It does not just focus on control engineering. It has got wide applications. Right? We'll see that. As you can see here, Matlab is matrix laboratory. Just a second. So Matlab is short for matrix laboratory. It's a numeric computation software for engineering and scientific calculations and applications. Used for circuit theory, filter design, random processes, control systems, communication theory, right, and so much other things. It was launched in 1983 by MathWorks, and it was one of the first commercial packages for linear algebra. Right. Then later on, it developed itself, and we are all familiar that today, as of today, with the launch of this 2021B version of the Matlab, there are so many areas in which MATLAB can be used or maybe helpful. Right? It is basically built on block system. That is, you have got packages called toolboxes. That also you must be familiar with. There are different packages. Let us say for electronics, you can use one package. Let us say for control system, you can use some package. For aerodynamics, you can use certain packages, right? And depending on what packages you select, company generally quotes you various prices, right? It is basically a high-level programming language. It contains a very good number of built-in functions to efficiently deal with matrices, numerical computations, symbolic mathematics, and apart from that, it has got a very nice GUI interface, Simulink and Simscape, to design linear and non-linear devices, systems in engineering, in all kinds of engineering, right? Just let us have a look at the broad capabilities of MATLAB, right? It can do data analysis. It has got graphics, right? It has got algorithm development capabilities. You can design algorithms for desktop and embedded applications. It has got a feature to build an app, right? Desktop and web-based applications. It has got compatibility with Python, C, C++, Fortran, Java, and other languages. So you can interconnect it. Hardware. So this is where you were talking about that hardware to connect. You can connect MATLAB to hardware, right? Then parallel computing. You can perform large-scale computations and parallelize simulations using multi-core desktop GPUs, clusters, and clouds. So basically, if suppose you have some applications which requires more amount of processor energy, right? Or a single processor is not capable, you can use parallel systems to perform the simulation of a same, system. Or you can also use server-based or web-based or cloud-based servers, right? Which can, like the server, you may have a powerful server somewhere else. You can get the license of MATLAB, do the simulation on that server, and get the results on your desktop. So your processor is not required, but you can utilize that thing. These are all paid services, of course. Web and desktop development. You can share your MATLAB programs, right? You can share your MATLAB programs with other users, maybe other experts for solutions, maybe for some sharing purpose, etc. And MATLAB in the cloud, as I told you, you can run it in cloud environment. Even if you don't have, let us say you have a incompatible PC which cannot install MATLAB, right? Maybe some small PCs which are just used for internet purposes and other things. What you can do is you can use it or run it in the cloud itself. So MathWorks also provides a cloud where you can do your simulations and other work online with a license, right? Of course, this Azure services are also included with this MATLAB these days. So these are the broad applications as I had taken from the MathWorks website. Right, you can see wireless communications is one part where it is useful. Power electronics is other domain in which we are interested in as such. Right. Third is this control systems. And control systems, this is also a part of interest to us. These two things combinedly, helps us to develop a whole power electronic system. More detailed information, you can visit this website, mathworks.com, and get other details. Those who are interested, but I believe most of you must be knowing these things. Signal processing, autonomous systems and robotics, advanced driver assistance systems, digital twins, artificial intelligence. There are so many areas of application for MATLAB, right? There is this Simscape. Apart from this Simulink, Simulink is, I think, almost every one of you is aware of Simulink. Simscape is another part of MATLAB wherein you can, add up support for this 3D mechanical designs for your product or for your converter designs. You can do non-linear simulations here, right? You can design, you can model your switches, non-linear switches here, right? You can import this models and data from other softwares, like import assemblies from CAD software. Let us say you are making a solar inverter, just for an example, right? You have prepared the circuit and everything, but now you want the enclosure. So you ask someone to make that enclosure. So a mechanical CAD design has been made. You have got that enclosure and everything. You can integrate it with this SimScape and ultimately get the whole simulation done, right? And get the results at how it will behave and all. The environmental and lifetime analysis, which Sir was talking, I think, in the previous lectures, right? So those things can be done. Now, next important software is Plex. Now, I'll ask a counter question here. How many of you know about Plex? Are there people who know about this software that this exists?
I don't know, sir.
Is anyone else like? Is anyone there who knows that this software is there? Okay, I believe that many of you might not have heard of this software because this is a specific software for power electronics, right? See, Matlab, as we are talking, this is a software. You can see it is used in general for all kind of applications. There are many other applications apart from this. This is just an overview, right? But Plex is a specific software for power electronics system. Now, those who are working in power electronics domain and those who are actually working with this, Plex is a very important software for you. I think in Agrawal sir's lab at IIT Mumbai, this software was purchased, right, Wani ma'am?
Yes, yes. In Apple Lab, it is there.
Yeah, in Apple Lab it was there, no? As I remember. Yeah. So this is a specific power electronics use software, which is very useful to deal with this power electronic systems. So what
very good for thermal
yeah.
aspects.
Yeah, that's what I have.
Very good for thermal aspects also.
Yeah, that's what I have included in this third point. So if you can see, what are the benefits we'll see? So this is a simulation platform for power electronic systems. The main important thing is it is interoperable with Simulink, right? If you design your system in Simulink Matlab, you can import it here and mainly do your thermal, magnetic, and loss analysis. But it is one of the best softwares to do thermal analysis of a power electronic system. And as we all know, thermal design is very important in power electronics. As much importance we give to the control design and maybe to the other design, the same importance you have to give to thermal design. Because I believe 60% of the power electronic systems fail due to thermal design problems. Right? You'll design a converter which operates very fine, results are excellent, maybe efficiency is very good, everything is good, but ultimately you start running it and it will get blown off as soon as you run it for maybe, let's say 10 minutes, 15 minutes, 1 hour, something like that. Why? Because of these thermal issues. Second cause is this magnetic issues, as we are discussing EMI and EMC. So this software is very good for thermal analysis. Plex scope. So Plex scope, there are different user interfaces in this software. One is Plex scope. Scope is basically used to extract the waveform. The scope, oscilloscope, what we call it. Right? It can extract the waveforms of interest, examine the data. Built-in analysis tools. They provide steady-state operating points for open loop and closed loop transfer functions. Right? Then it can also extract the state space matrices of the system for advanced analysis. Next, you have this simulation script, which can change the parameters. In simulation scripts you can change the parameters online. Like in case of Matlab, it is difficult for you to change the parameters online, right? You cannot. Meanwhile, the simulation is running. You cannot change the parameters. Here you have that advantage that you can change the parameters within simulations also, and you can of course extract the data for post processes like in Matlab. Then you have this Plex coder. Coder can generate real-time C code from a circuit or a block diagram. These features are generally available in most of the software these days, including Matlab and others also. Okay. This is an example of a flyback converter with 2 secondary outputs designed in Plex. Right? You can see a very common and very simple design. And the main part what you want to focus is this one. So we can see here, this is the transformer, right? this is the transformer designed here with thermal and core losses. See here, you can see the core loss has been extracted, right? An equivalent circuit has been done. It's not just a transformer, so you can extract all the losses and do the analysis with this. Even this is the switch, like the switch has been modeled, and here you can take out the thermal losses and all this from here. Right? The features. There are certain features of Plex. Let us see those. Plex block set. Block sets are a unique tools for fast simulation of power electronic circuit within the Simulink environment. So you can use this Plex block set in Simulink environment as well, right? So if you are using Matlab, you can just use this block set of Plex in the Matlab Simulink environment. You have this Plex standalone software also. You have this coder as we discussed, which can generate C code from a simulation model. Plex PIL, it is a complete solution for processor in the loop simulations. Those who are working with such kind of designs where processor in the loop is required, you can use this kind of you can use this software to do those simulations also. Plex web-based simulation. This is a web-based service wherein you don't need to download the whole software. You can simulate it online as well, right? You can also develop models offline and then upload it on a simulation server, whatever. You can do it both the ways. And sorry, excuse me. Yeah, you can also use Plex RT boxes. These are actually some hardware. Right? It's a kind of a hardware which is basically a real-time simulator which can be used for hardware in the loop, HIL, and rapid control prototyping testing of complex power electronic systems. So you can use this as a hardware in loop and maybe do rapid control prototyping also. If you have made some power electronic circuit, like if you remember yesterday we had seen that video about the PCB manufacturing. There in the end they were using a circuit to test the test points and the continuity of the wires inside that manufactured PCB, right? Now those who want to go for a trial version of this, or you want to try this, or you want to study this, previously they were giving only 30 days of trial license, but these days they are giving a 90-day trial license upon request, right? So those who want to try it, 90 days, 3 months is, I think, a sufficient time, and you can definitely, try this. Trial licenses are free, full functional, and this is the important thing here. They are fully functional. It is not that in trial functions the functionality is limited. They are fully functional, so you can, download it, learn it, and also they are saying that it can be renewed upon request. I have taken this information from this their website ppmpower.co.uk. You can visit that and get more details. So if they are renewing that upon request, I think it would be a good thing to learn and use it. So mainly this software, as I told you, is very good for specifically for power electronics and very good for thermal analysis, right? Next commonly used software is Pcm. And as I was discussing, many of you must have used this software as well. Pcm is a simulation software specifically designed for power electronics and motor drives. This is also a very specific software, broadly used for power electronics. Of course, it is also used for electronics purpose, because most of the time you'll see that undergraduate students or maybe most of the institutes, they are using this software for the trial versions, student versions, etc. or the demo versions for simulating this microcontrollers for 8051 simulations, maybe this AVR and PIC simulations, etc. But apart from that, this software is also very useful for power electronics simulations. The main advantage, as you'll see, is that it can simulate non-linearities very well. So if you are simulating, let us say, an inverter in Matlab, you need to do much of the coding, and you have to develop a non-linear model specifically, code it, and do some extra work in order to get accurate results. Otherwise, you will get idealized results in case of Matlab. in case of PSIM, you'll see that there is one other software also. I'll discuss it here. This PSIM has got capabilities that they already developed. These non-ideal models, right? Non-ideal models are readily available here, and you can directly use them to simulate your circuits to get accurate results, right? Rather than those idealized results. So it provides a powerful simulation environment for power electronics, analog and digital control, magnetics, and motor drive system studies. So if you are also into electrical drives, right, power electronic drives, that is then also this software is very useful to you. Next is if you are into this magnetic designing and all, that is then also it will be a helpful tool. SPICE, as I was discussing, it's basically short for Simulation Program with Integrated Circuit Emphasis, which was developed right way back around in 1970s or 80s. I remember 70s, I suppose, say 60s or 70s. I don't remember exactly, but after that, it was based on that modeling thing, right? Mathematical equations, calculations of them, and then it got enhanced day by day, right? After that, these days SPICE 2 is available. Then even SPICE 3 SPICE 2 is commonly used these days, but most of the time, right? Developed at University of California at Berkeley, and now SPICE 3 is also available. But most of the time, this SPICE, now it's an open source software, but these days SPICE was actually purchased by PSpice. So now PSpice is available. It was purchased by Cadence, I suppose. See, I'll just, yeah, this one. The increased utilization of PCs has led to the production of PSpice, a widely available PC version distributed by the Microsim. Yeah. So it was basically purchased by Microsim, and they are now licensed it, and it is available as Orchid these days, right? So what can PCM do? So you can see here, PCM can do power supply design. So if you are designing power supplies, right, based on power electronics, you can do power converter and inductor losses calculation in this PCM. Open loop and closed loop simulations are possible. AC analysis can be performed on switching models directly, and digital delays can be included to design directly in the Z domain. This is a very good advantage of this software, right? Apart from that, a library of PWM control ICs is also available for a full power supply simulation. So let us say if you are planning to use some PWM IC, you can directly get it in the software library itself. Similarly, motor drive design is also available, right? You can use the motor control design suite to implement sensored or sensorless PMSM or induction machine drive, right? A comprehensive electric machine library is also provided in this, along with the effect of spatial harmonics and saturation. Similarly, scripting and scheduled simulations are also possible in case of PCM, right? You can it provides a powerful scripting language that allows you to automate your simulations and analysis. Any circuit attributes and simulation parameters can be changed by the scripts, and simulations can run sequentially with initial condition being passed. So it's like all the kind of support you require for power electronics is available in this software. Of course, the details about this software, I'm already using this software as such, but more details and other things were provided to me by Mr. Vinay. He's power electronics support engineer in PCM. If anyone is interested for maybe for this trial versions or requesting this demo versions for this software or need some help regarding this software, you can directly contact him also. The details are given here. This is just for in case if you want help regarding this software, more help regarding this software. Right. It can also be, you can also directly contact the company as such for details. Because my institute, like Government of Gujarat, has already purchased Matlab and Nsys software for the 16 engineering colleges in Gujarat, and we are already licensed users of these softwares. So I didn't need to get all those details from here. But PCM we don't have this licensed version of PCM, so I had to request them for a trial version so that I can demonstrate here. These are the other things in which PCM can work. Digital control implementation, a very important part for power electronics. You can see C code can be automatically generated from the schematic for seamless implementation on a supported Texas Instruments C2000 series processors, that is 28335, 28337, or maybe 2879D and other dual core processors as well, or 6000 series DSPs as well. Right. Then you have the solar and wind power system. Those who are working in the field of solar and wind power system, there also a very good support has been provided. Sample MPPT and complete wind power system examples are also available. I'll show you possibly. Then wide bandgap devices. Those who are working with silicon carbide and gallium nitride devices. This is an emerging area in power electronics, as you might have been into touch with. Even my master's thesis was on this only, and I'm currently doing my PhD using this under this domain itself. So here also you can use this software for modeling analysis of these wide bandgap devices. Then multi-level switch models, magnetic design, and code verification. These all features are also available in PC. Okay. I'll just go through quickly with the features. With PCM's interactive simulation capability, parameter values can be changed and voltages current can be viewed in the middle of the simulation. This is a very, I like this feature very much, because when you are doing simulation in softwares like Matlab, you cannot stop the simulation in between, or you cannot change the parameter value in between of a simulation, and you cannot see what changes are done, right? Here you can do that manually, and you can see what effects you can get in the converter. Digital control module can help the design and simulate simulate digital power supplies. Right, digital control can be implemented in either block diagram or using custom C code as you wish. Then a built-in C compiler allows you to run or code use a custom code in PC. Right. Thermal module here can be used to calculate semiconductor device losses, conduction and switching losses based on the device information from the manufacturer sheet. This is again a very good feature that I love for power electronics in this software. That is, you can do the semiconductor conduction and switching losses analysis here based on the information from the manufacturer datasheet. You can directly use the manufacturer datasheet to import or to take the values from therein and enter it in the software, and based on that it will give you a basic thermal and switching conduction and switching losses analysis here. Right. These are just some of the screenshots of images showing how circuits are made in PCM and how their simulations or results can be obtained. You can see it here. It's an SCR based inverter and its output waveforms. Right. This is you can see converter design. Right. The scripting is done here. This is the PCM library. These are the elements and other things available. As you can see, buck boost, single phase inverter and other things. This is a single loop circuit made here. It's an VMC, I suppose. This you can see EMI analysis. EMI analysis can also be done in PowerSim. PCM. You can see this is the EMI filter and common mode capacitors connected, and this is the EMI filter design template. Right, you can change the values here and accordingly design an EMI filter. Right. Controller design can also be done. You can see different controls and how it can be viewed. Rapid prototyping can also be done, as I told you. Once you design, of course, this is for industrial use, not for academic use as such. But once you simulate a circuit, automatic code can be generated and it can be loaded into multiple DSPs or control cards for rapid prototyping. Right? These are some of the videos and some of the links available. I was planning that if I have time, I would have shown, but right now I don't think so. It will be good enough to show you all these videos. But of course, I'll talk about DSIM here, right? Before moving with PSIM, let me talk about DSIM here. What is DSIM? DSIM is a latest, a new software that they have integrated in PowerSim itself. Right, it is a part of PowerSim itself. But DSIM basically stands for digital simulation. This is, to be very frank, even I didn't knew about DSIM till now because I was not using the newer version. But that Mr. Vinay only told me about this and introduced me about this. DSIM is basically dedicated software or dedicated part of PSIM for power electronics, dedicatedly for power electronics. It is currently based on digital control of power electronics. You can use this to design your power electronic circuits and do digital control. I think let me see this video. Yeah, this video is an introductory video to DSIM, right? Hope this audio is being available in the presentation, right? You're able to hear the audio?
No, I am not able to hear. I don't know about others.
Yes. Audible?
We are able to hear the audio.
Okay, fine, no problem. So I'll start it from here. It's just a short video to introduce DSIM, and it's basically PSIM. Video is visible, na or not?
No, sir.
Oh, okay.
No,
sorry.
sir.
Yeah, understood. I was just thinking that thing. Just a second. Yeah, now it will be visible.
To get started with DSIM. So DSIM is our new engine, which is incredibly fast, but it also
visible now, na?
Yes, sir. Audio also.
Limitations. So to get started, let's look at an example circuit. We'll go up to help here. We'll go search help, and we'll look at an example. So we get into the example files here, and there is a DSIM folder. All of these are DSIM compatible. We'll grab this LLC here, and we'll take a quick peek. Let's run the simulation. So to run it, we go up here and we click the D. So this should get that overview there that says run DSIM. We'll run it and we get our results here. So exact same kind of interface when looking at PSIM simulations, same interface here, and this is the DSIM results. So how do we set that we go for 100 milliseconds, and what other engine settings do we need to define? Well, let's click on the clock and come in here and we'll pull up the results again. So we simulated for 100 milliseconds. That's
I'll interrupt here. You can see here, this is DSIM is a part of PSIM itself, which they have introduced in the newer models or newer version, the latest version of PSIM. This digital simulation, if you work with this PSIM, this is the module where you are working, right? And if you work with DSIM, that is power electronic digital simulations, you can simulate those parameters here in DSIM, right? That is the difference. You just have a quick look so that we can move further.
The end time right there. Maximum time step. Maximum time step deals with the max step that the engine will use when simulating the passive elements, or sort of the power stage. The way DSIM works is the switches are treated completely separately. This is one of the reasons why it's so fast. So the maximum time step here is more so with the external components. You'll need to reduce this if you have very small values out here that you're trying to study. So small capacitances or parasitics out here that you'll need to look at. So higher frequency interactions in the passive elements, you'll need to have smaller max time steps. Relative error is another setting also on that same idea, and the maximum display time step will help you reduce the size of your output file. The other thing you should notice right away is that we are using pre-built switch modules in DSIM. So DSIM does not allow for a discrete switch to be placed in any particular topology. So we'll notice right away we've got all of these MOSFETs and things in the library. We can't use these. So in order to make sure that you're building a simulation out of parts that are DSIM compatible, head on up to options here, go to settings, go to advanced, and then uncheck the PCIM and spice boxes. So you'll just be left with DSIM elements in the library. And you'll see right away we have the options here between all these various components. Now, we're not limited to just this sort of configuration. We can still build any kind of topology we want as long as we are using these blocks. So
Yes.
we can, let's have a look here. So we can build like an MMC with stacked blocks. We can put a diode bridge at the front, you know, whichever we're looking to do. As long as we use these blocks, we're okay. Other things to comment on is how these blocks are gated. So in PCIM, we can use an analog comparator with a carrier, but that has now been abstracted. So if we go into other here and switch controllers, these are all of the switch control elements that you can use to turn on and off these particular blocks. So if you're using, so this one is handy. It automatically builds a 3-phase modulation waveform for 2-level and for 3-level at whatever carrier you want. All you have to do is provide alpha, a normalized alpha and beta. So between -1 and 1 on both channels there. And you just wire these up. There's a lot of examples that cover the use of these elements. And you, again, just head bound back to search help up here. And let's maybe look for an MMC example, MMC, and we can see some of these in here. So there's a 3-phase inverter with a 9-level, we're 4 cascaded H bridges here. So we can run this again, just click the DSIM button and we've got the results right away. And there's our output voltage. So that was pretty easy to do. And again, we're looking at building up the power stages out of these specific components. And then the control algorithm, we got to make sure that the control algorithm is digital control only. So that means Z-domain transfer functions and discretized elements, because that's the way the engine works. Other things to cover here is if you go up into the menus, you can look at the check elements here. So if we go check elements, we should be able to use this menu to look at elements in a particular simulation to see if they're supported by DSIM or PCIM or all those sorts of things. So if we go, which elements are supported by DSIM? Well, since this is a DSIM simulation, they're all going to be here. But that's another way of looking at a simulation you may have built for PCIM. If you want to check to see if it works with DSIM, is to use those options. Okay, so that's it for this video. Do pay attention for other videos that go into simulations with DSIM in more detail. But the basic idea is make sure you use the pre-built blocks for your switch modules. Make sure you use the motor models that are supported. So you can't use any the full library of machine models with PCIM is not compatible. You have to use these. There's only these 2 models right now. And then do make sure you use the proper gating control elements, that your control loops are in digital control, and you should be good to go. And do send us any questions if you have them, and we're happy to help in that regard. Okay.
Okay. So that was DSIM. This is the latest development in PCIM. That's why I thought of showing you this video. And no, there are other getting started with PCIM. You can go to YouTube and watch these videos if you're not very familiar with this. Right. There is also an example given here. Boost PFC example using PCIM auto core generation for 2833X series of DSPs. I'll just show you this very quickly. I'm not going to show you the whole video because it's almost 8 minutes long. But you can see
F2833X floating point line of processors from Texas Instruments. As a starting point of the
just let me mute this. You can view this video on YouTube later on your convenience, but you can see this kind of circuits can be made. Simulation results can be obtained, right? This is the whole digital control circuit that they have made here. Okay, and then after configuring for the configurations here, what different parameters you want, then you can use this to select Yeah, this is see. As you can see here, this is the 28335 block here. This one, right? So that is Texas Instruments 28335 DSP processor. As you can see, it's been integrated, and you can make the schematic this way. And ultimately, yeah, here you can see the target selection using sim coder. You have to select FA2833X target. You can select what you want accordingly, and then finally you can generate code to dump it in the. Here you have to select the GPIOs and other configurations for that DSP. And everything is shown in the video. You can see it later on. You can select the frequency, hardware target. Okay, and yeah, these are the simulation results and all. And see, this is how the whole code is generated. You can just have a look at this. There's a C code that gets generated from this PC, right? And you can use this to load it in the DSP processor. Okay, so these are the facilities and features of PCM and DCM. So let us move ahead now. Next software that is available for power electronics is Nsys. Nsys, it is not a dedicated software for power electronics. Again, it is again a paid software, right? But it is mainly used for simulation. It's basically simulation and modeling software used for motor design, its analysis, and finite element analysis. Particularly, those who are working for FEA, like it is a useful software therein. Power electronics and thermal analysis is also possible in Nsys these days, right? Since we are using it here in our institute, we are licensed users of this. They have got two types of licenses. One is basic license and one is research license. Research license has got many capabilities, and of course it is very costly. Research license, as I remember, it cost us around 5 lakh per license. So our institute has got 5 licenses research, and I think other around 100 general licenses. So research license has got many other capabilities. Those who are working on research or doing their research can use that license. So these are the major areas where it can.
Sir, simulation can be performed using this Nsys or not?
Yes. We are coming with that. Okay.
Okay.
Yeah, it's as I told you, this is a simulation. Just a second, let me take the pointer. See, this is a simulation and modeling software. You can also model things. You can also simulate it, right? So what are the application areas? As I told you, EMI, EMC analysis can also be done. We'll see those. So these are the general areas where this software is used: fluid engineering, material, right? Then you have electronics, autonomous vehicle simulation, embedded software, photonics, etc. Structures, even. So this is Nsys software is used in mechanical engineering, in electrical engineering, in civil engineering, right? It has got wide use. Again. That's why I told you it's not a generalized software. So let us see the use for power electronics. To be very frank, this presentation, I had requested the Nsys support person for our institute for this Gujarat region. I think he is the support person for Maharashtra and Gujarat region. I requested him to give me some slides which can show up, good this thing, because my Nsys software is basically a licensed version and it is available in my office desktop PC, in my college desktop PC. So I would not be able to access it from here right now. So, see, this is a multidisciplinary power electronic design requirements. As you can see, that system and circuit design, electrical team generally, or we as power electronics or electrical engineers do the system and circuit design thing. Mechanical team can do the reliability engineering, right, and enhance the PCB reliability. This can be done by the electrical or mechanical engineer as well. They can even do the structure design, and software team does the embedded control part, right? Electromagnetic and thermal team, they generally do the magnetic analysis, thermal management, and EMI, EMC of the converter. So these all things can be done in Nsys, right? You can see languages modeling can be done using SPICE. It is interoperable with these things, right? Multi-domain model libraries are available, as you can see. Co-simulation with 3D physics. you can do the motor design or electromagnetics part. You can do the fluid design. You can do the thermal design. You can do the mechanical design. Right? All of them can be combined in a single software. Right? A reduced order model creation is one of the features. And Nsys CAD, it's a software where you can design your controllers and simulate them. You can do the software embedded software integration using this CAD. So you can directly connect it with the processors as well, direct code generation. System model interoperability, as I told you, that it is interoperable with third-party systems like MSync, Simulink, GT, Dymola, etc. So even you can use it with Matlab, integrated with Matlab as well, right? This is the regulated flyback converter design, as you can see. So you can design it, right? Simulate it, do the thermal analysis, do the EMI, EMC analysis, do the check the graphs, right? Simulate it, change the parameters, everything can be done. Do the converter design, and you can even, initially Nsys was not that much suitable for power electronics, but nowadays they have integrated all these facilities here, right? So these are the things they are using it for advertisement. Frankly, I'm not here to advertise anything. We are just here to understand the things, that which are the software, which are the tools which may be useful to you while doing your work, and you may select a proper software depending on the features and other things, right? So you can see here, multi-domain circuit analysis and circuit simulation is available. As you are asking me, sir, whether you can simulate or not. Yes, we can do that. Complex system models, model libraries, and reduced order model workflows are available. Different levels of accuracy can be obtained, right? See here, small, electromagnetic, power magnetic component design has been done. You can see how it simulates and tells you, right, with respect to time, how is it working, right? This is an electronic transformer design, right? This is, you can see, reduced order modeling to account for component interaction. This is a PMSM, right? Model with a power electronic converter. So the whole drive has been modeled here, as you can see, this one, right? You can, the benefits are that you can reduce the hotspot orientation below thermal limits, etc. So you can check what are the heat limits and other things using, right? See, this is the thermal analysis performance. How you can see this is an IGBT or maybe some switch module. You can see the heat analysis is done here based on a simulation. You can see this also. So this kind of analysis can be performed. This is also good software, right? This is
Sir, how we can import our model? Suppose I have a DC-DC converter, which is a model in the Matlab. Then how we can take that file in this particular Nsys? We need to model once again in this Nsys.
No, see, when I say that this is interoperable, right? When these people say that it is interoperable, it means that you can either import or export models from one software to another. It is not just for Nsys, sir. It is a common thing for all the softwares. When you say some softwares are interoperable, it means that you can, there must be some function in the software wherein you can import files from other softwares. So let us say Matlab extension has got .m or maybe other extension. That extension can be imported, and that model will be converted into your Nsys extension file, and then you can do the analysis on that. And again, you can export that file, or maybe you can import the file in Matlab if it is compatible, right? It is true for all the softwares, sir.
Okay.
Yeah. So this is the thermal analysis part, as you can see. This is embedded system control. You can see this is the whole circuit. Yeah. So this is the whole circuit. SCADE is used to design the control. This is the certified, this is the code which has been generated. This is the extensive model library which is available, right? This is the conducted EMI EMC library. You can see here, this is EMI EMC, right? This is the library they have given for EMI EMC test. So you can do the near field and far field analysis for EMI, the one which our previous speakers were also discussing, that what precautions we need to take to reduce this EMI EMC, keeping the ground and this planes parallel. So once you do that thing, you will be able to understand that if I'm putting some component somewhere or maybe some wire somewhere, what kind of electromagnetic field and noise has been generated, right? And accordingly you can modify your PCB to accommodate or to reduce those things, right? Similarly, import of electronic CAD format. See, if you are designing, let us say, your PCB in some other software, like let us say Eagle, KiCad, maybe OrCAD somewhere, you can import those CAD formats here and then do the analysis, right? Physics simulations in a single platform. Then you can do the lifetime prediction, right? As I don't remember the name of like I think it was Madhuban sir, na? Madhu Babu sir, I think. Yeah, Madhu Babu sir was talking about this lifetime prediction and how they work out the lifetime prediction, how they predict the lifetime of a device and all. So this can also be done here for the design PCB, right? Then this, let us see, just quickly see an example of brushless AC motor control system done in Nsys. You can see here, this is a brushless AC motor control system. This SCADE does the controller design, embedded software controller, which has been created using Nsys SCADE suite. There are different suites in Nsys. SCADE suite for controller design, right? Then simpler library for simpler or twin builder, as it is called, for the simulation part, right? RM Expert. RM Expert is a block set to design machine specifically. So let us say you want to design a electrical motor, new type of electrical motor. It can be done in RM Expert model. Right, module. So you can purchase these modules separately as per your requirement. And this is the mechanical load which has been designed. You can see here. So this machine part has been designed in RM Expert. So this part has been highlighted here. You can see this is how the machine, the slots, the winding and everything has been designed, right? It is included as the RM Expert project, RM Expert _ BLAC. So that is the name being given. And then it can be integrated in Twin Builder. Similarly, this is the inverter model or the converter part here, as you can see modeled here, right? And again, it can be imported to the Twin Builder to simulate it together. So you can make this inverter model in separate model. You can make this, design this motor in some other in the other part. Then third thing is you can this load can be designed separately. You can see this mechanical load. It's not just an electrical load; it's a mechanical load. You have been given how much torque, how much load, mechanical load has been given, and how much torque it gives, how much friction and other things. Those all things can be programmed here, like inertia and other things. And similarly, SCADE, this SCADE part here, this is the controller part. Simulator time, reference speed, inverter switching period, everything has been defined here. And this SCADE suite is basically the controller design. And all of these things can be integrated in this Twin Builder to do the complete simulation. So you can understand how the system will behave. Right? These are some of the simulation results, as you can see, for the motor currents or the rotor speed. Right? You can see how this motor currents become 3-phase after here and get stable. This is the graphical user interface of Nsys. Once you open up Nsys, it will look something like this. This is the project manager window, history tree. This is the menu bar. These are the toolbars. This is the menu bar here. This is the property window. This is the modeler window where your actual model will look like. Right? This is the coordinate field, status bar, message window, and progress window. These are the available machine types in Nsys. These are already available as predefined or pre-built models. You can modify it according to your requirement. You can see PM, synchronous motor, BLPM, claw pole alternator, DC machine, 3-phase induction machine, PM AC, PM DC, non-salient machines, salient machines, universal motor, single-phase induction motor, SRM, everything is available. Right? This is the magnetic plot for transformer. You can see create field plot of MAGB. You can see this type of how the this flux will be seen inside this magnetic core or the transformer core. It can also be simulated here, and you can understand what are the different levels of the flux here. Okay. So this was all about Nsys. Nsys is also good software as such for power electronics and electrical drives simulation and design. Right. Those who are interested, also go on this. So if you are particularly working for a drive project, I would suggest, which contains motor, I would suggest you can go for Nsys, because there you can even model your circuit in Matlab, import it here, model the motor in RM Expert, and then combine it to check the working of the system. Right? Now, this software will quickly overlook because LabVIEW is another software, right? It is again a paid software, but this is specifically for designing and interfacing things. This is specifically for designing interfacing and human-machine interface. Okay, human-machine interaction system can be designed using this LabVIEW. It is basically for collection of data and maybe interfacing with each other. So LabVIEW, it is Laboratory Virtual Instruments Engineering Workbench, system engineering software for applications that require test, measurement, and control. It is less into power electronics domain, but may be useful sometime, right? When we are into the test and measurement things, right? It offers graphical programming approach, which can help you visualize every aspect of your application, including hardware configuration, measurement data, and debugging, right? For real-time control, LabVIEW is the best tool available in the market. It can connect with, this is the most important feature of LabVIEW, that it can connect with multiple devices to acquire data from sensors and control actuators based on the process data, right? So when you want to connect multiple things and acquire real-time data, for real-time control, LabVIEW is one of the best softwares available in market. You also have a book published by, I don't remember the publication, but there is a book getting started with LabVIEW. You can also purchase that book, or maybe request inspection copy. I think they are also specific giving this. I do have the specimen copy of this getting started with LabVIEW. It's also a good book. Okay, so now let us break the chain of this paid software. Let us come to open source softwares. Now, those people who maybe cannot afford or maybe do not have these facilities, or the paid softwares are not available, right? Acha, before that, I was Minimum had requested me one thing, that we had just had a talk that this PCM, right? PCM software, yeah, this PCM software, which we are talking about, right? This software initially was very costly as like Matlab, but these days they have reduced their price drastically. And as I had inquired just day before yesterday, the person told me that these days this software is available at a very less cost. That is around if you go for a single license, it is costing around 1 lakh rupees. And if you go for, let us say, multiple licenses around 20 or so, they are just giving it a cost of around 3.5 lakhs for 20 licenses or so. So that software has been quite low price these days. And even as in academics, what you can do is you can request them for a trial software or maybe for a teaching license as well. They also sometimes upon special request provide you teaching license, so that you can ask your students to use demo version and you can use the teaching license to teach them with some amount of limited features and examples. Okay. So yeah, so let us move to this open source softwares. Now Matlab or PCM, what are the major, I'll not talk about PCM, but let us say Matlab, because Matlab is a very general domain software used in almost all the branches. So hope I'm not running late with time. So Octave. Octave is a open source software which is closer to Matlab in terms of compatibility and computational ability, right? Most of the project which you develop in Matlab will also run on Octave. So you can, if you have some projects developed in Matlab, you can download and install Octave and run those projects there. Major features: handle powerful mathematical syntax, equipped with plotting and visualizing tools, just as Matlab. Open source and is compatible with all types of OS. Developed for complex linear and nonlinear numerical computations. It can run interactive and batch jobs, and it is compatible with MATLAB script modules written in Java, C++ or Fortran. So it is compatible with almost all the languages. See, this is the interface of Octave. You can see it is kind of similar to MATLAB. For those who are using MATLAB, This will be, not much new to them, right? You can see this is the coding part and this is the workspace, right? This is the project folder. This is Octave basically. You can see the graphs here. So Octave is a very major and very useful software in line with MATLAB. Apart from Octave, a very good and very impressive software is Scilab. Scilab is also freeware software, open source software. It is one of the major alternatives to MATLAB along with Octave. Okay. Scilab's library and files are based on analysis of data, development of complex algorithms, models of previous computations. Mathematical computations are based on progression, regression, Fourier transforms, differential and integral analysis, ODE, right? Data can be visualized using any of the following like pie charts, line, bar graph, histograms, MathML annotations, etc. So Scilab is also a very good and very effective software widely used by open source community. Right. Main features: free and open source, numerical computation providing a powerful computing environment for engineering and scientific application. It is again like MATLAB, a high-level programming language with access to advanced data structures, 2D and 3D graphical functions. So you can use advanced data structures and 2D, 3D graphical functions as well. It can be used for control system, signal processing, application development, 2D and 3D visualization, optimization, statistics. All these functions are supported in Scilab. Again, this is the console or the main GUI of Scilab. As you can see, very nice GUI, similar to again Octave and MATLAB. So those who are working with MATLAB, it won't be very much difficult for you to switch to Scilab, right? And it's an open source software, so free of cost. You just go to the website www.scilab.org and download it. That's it. Install it. You can use it in any OS, Linux or maybe Windows or maybe Mac. See, these kind of functions are available in Scilab. As you can see, numerical analysis, data visualization, app development. Even app development is supported in Scilab, like MATLAB, right? Algos development, algorithms can be developed here. This is the equivalent XCOS, that is basically Simulink equivalent of MATLAB.
Hello.
Like, yes.
Hello, sir. Sorry,
Yes.
sir. Sir, can you take some questions now? Because next speaker will join.
Yeah, just give me some 5 minutes. I'll finish up the presentation quickly. Okay, so that we can take up.
Okay, sir.
Yes. Yeah. So this is the equivalent equivalent to Simulink. You can see how you can simulate. This is the libraries, right? It is called Atoms. Here you can find the libraries for almost all types of things. Then certain other softwares. Julia is one of another such kind of software, right, which can be used for alternate to MATLAB. Maxima is one of the software, but these are not that much popular. Popular is Octave and Scilab are very popular. In Maxima also you can do this type of coding, this kind of graphs and mathematical equations can be used here. Next important software is SQL, which I was talking, which is developed at IIT Bombay. Right, it's a general purpose circuit simulation software developed at IIT Bombay. It provides a GUI for schematic entry and plotting. Simulation examples for electronics, power electronics are or particularly suitable for teaching engineering courses are included in the package. This is made in India by software by IIT Bombay. Dr. Patil has mainly made this, right? And everything is available on the IIT Bombay's website here, right? Everything is available. User manuals I have included here, but right now since time is not there, I'll not open it right now. You can see that. Now, the last thing which I will discuss very quickly is designing PCB. We had already discussed what is the importance of designing PCB. Right, these are the steps of designing PCB. I'll not go into details of that because already you had those sessions previously. So I'll just discuss the major software. ORCID is one of the major softwares for simulating basic electronic circuits and preparing PCB. ORCID is widely used in industry. Right? These are the different modules of this ORCID. ORCID Capture, PCB Designer, System Integrator, Security Checker, etc. This is a professional software which is used to design PCBs. Right? This is a paid software. Similarly, KiCad is an open source software for PCB design. This is a very nice software and widely used software since it is a free of cost or open source software. It has got a wide community. It has got schematic capture to prepare designs. This is the schematic capture, right? This is how you create a schematic. This is KiCad PCB layout. Here you can see you have a PCB here and the 3D viewer of the PCB once you make it. So these all facilities, this is a free of cost open source software. Design Spark is another software which is also free software. It also has this kind of schematic capture which you can use to prepare schematic. This is how you can prepare the PCBs here, and this is the libraries which are available. You can create your own libraries or use ready-made libraries. You can export whatever types of Gerber files you want, right? This is the bottom layer, I suppose. This is bill of material. You can also generate bill of material for your project. And similarly, you can export designs to SPICE simulation software as well, right? Another software is Eagle. Eagle is also a PCB manufacturing software. You can prepare PCBs in Eagle, right? These are the quick schematic editor, PCB layout editor. This is how it looks in Eagle, right? You can just have a look. So, anyways, I'll end it with this. These are the I wanted to take these softwares in bit detail of this PCB design, but due to this time limitation, I'm not able to do it. Anyways, but please feel free to ask questions.
Hello.
Yes, ma'am.
Sir, if I design any circuit in a multi-sim and if I want to model it in Altiboard, then what are the steps should I follow?
Okay, see ma'am, when you do it in multi-board, so basically you are using NI's multi-board and Multi-board, right? Multi-sim and Altiboard. So it's also a nice software to actually have, I wanted to integrate it, take it here also, but I could not. Multi-sim is a proprietary software by National Instruments. When you make that design, the whole schematic in multi-sim, then you have an option to export it or to change it to Altiboard. So the whole schematic, right, which you have in case of your multi-sim, that will be exported to Altiboard, and in Altiboard you will find all the footprints. Like in schematic, let me just open up this thing. See, yeah, like in schematic, if you see, you'll see this kind of diagrams, right? I think these are more clear here. You can see this kind of diagrams here, right? So what you can see is, let us say this is a transformer, or maybe this is a capacitor, there is an inductor. So here you'll see it as a capacitor. Once you transfer from file or preferences, in the menu itself, you will have an option to change over to Altiboard, right? It is available in all the softwares, all the PCB CAD softwares. Let us say if you have KiCad, there is also an option there. If you have OrCAD, there is also an option there. If you use Eagle, let me just see. My Eagle is open here. I'll show you. See, I think you will be able to see. This is my schematic. This is my own PCB made. This is my own schematic which I had made. This is a silicon carbide MOSFET driver, right? High speed for which can operate up to 200 to 300 kilohertz. I had tested it for 200 kilohertz. You can see I had drawn this schematic here. Right, and you can simply switch to board. You can see this option here, ma'am. Rimi, ma'am.
Yes, sir. Yes, sir.
So when you switch to board, you do this. See, directly a board will open here. In Altium, in this, even if you go for Altium, it is also PCB design software. Even if you go for multi-sim, there also you'll get this kind of option. So you can directly switch to board. Then what you will get is you will get this kind of board here. All the components will be laid up here. And what you have to do is you have to simply take up these components and place here and accordingly route it here using this. So see, this is these are the bottom layers, wires, edge, pad, everything can be seen here. So this is how your PCB can be done. This is the PCB that I had designed. So there you will get such kind of option. You make PCB, schematic there, and then switch to the Altiboard. But make sure in any kind of a general instruction to all of you, make sure that whenever you make this schematic, be sure that a footprint is available for that schematic. Okay, make sure that footprint is available for the schematic. If you let us not go into details of that, but be sure that footprint is available. Otherwise, you won't see that in the board editor. All right.
Thank you, sir.
Yeah. See, this is also, see here, this is a Design Spark software, right? Here you can see this Raspberry Pi is modeled here. Okay. And once this schematic is made, then you can switch it to the board view, and the board view will look like this. This is a design PCB, right? So you can design this, can select this pads, right? You can move them, see this way, right? Right. You can move it this way, right? Whatever design you want. Okay. You can move this pad. So you have to design it this way. So this is where you work with the PCB. You have to actually zoom it in and properly design this. If this is the pad, right? I have to place it properly. Right? There are some changes to be done. This is just an example model. Yeah. Any other questions? Other questions for participants?
Yes, participants, you can ask your doubts. Anyone?
Actually, I could not took up this PCB design part properly because of this time limitation. Actually, we had already started the session late, so it got bit of messed up. Otherwise, I would have been able to complete it properly. Anyways, this I will share this PPT with you, sir. I'll share the PDF and other resources, so the participants can take the advantage of this. Most important thing in the end, I'd like to conclude is that for power electronics simulation, depending on your application, on your project, on your this thing, what we say, on your on the circuit what you are working on, you have to select proper software, that which software will give you the best results and quick results, right? So I discussed almost all the softwares. Nothing was intended for you go only for this software or that software. I had in general covered all types of softwares. Only intention was to make you aware that what are the features available in different kinds of softwares and which can benefit to you for different types of applications. That's it. So I hope I was able to convey all the information and you all learned good things from this session. In the end, I would like to thank Mini Rajiv ma'am, Dr. Mini Rajiv, Dr. Mini Nambudribad, Abhishek sir, and the entire FCRIT team for conducting this FDP and giving me a chance to share my thoughts and useful knowledge here with the participants. And I appreciate that this is a really nice FDP, focusing on the practical aspects. And I wish good luck to every one of you. Thank you, sir. Over to you.
Okay, thank you, sir, for accepting our. Okay. So thank you, sir, for accepting our invitation and for giving details insight into the simulation tools like Matlab, Plex, PCM, and DCM, etc. Sir, session was really interactive and informative. So once again, we would like to express our gratitude to Professor Harshal Wani for conducting this session. Thank you, sir.
Thank you very much, sir. Thank you, ma'am. So I'll take a leave.